So this lecture is about tissue transplantation. The reason why it's been put in the renal block is because kidney transplants are one of the most common types of transplant procedures in this field. Before I begin, I just want to give you some historical perspective about the subject. So when the clinicians and immunologists first tried to start these experiments of transferring tissue from one animal to another, this was the age of immune research, which was very basic, but we had no understanding of how T cells recognize antigen. That's from the immunology side. From the medical side, the reason why these type of procedures were being developed was this was immediately after the Second World War, where soldiers who came back from battles suffered horrible injuries, particularly burns on their skin that had to be reconstituted. During that time, the idea of transfusing blood from different individuals reached its height, and we had an understanding of the ABO blood system, which gave us an understanding that between individuals, there are certain tags within these different groups which somehow our bodies recognize. So the objective of this lecture is to talk about the different types of grafts which are used in clinical practice today. The genetic basis for acceptance of a graft or rejection, which I must emphasize lies with the type of HLA genotype, because this is what is presenting antigen and what is seen by the reactive immune system. And then to talk about the methods we use to determine the types of identity or non-identity if we try to do transplantation. This isn't such a big issue now with the advent of anti-suppressive drugs, but there are certain types of transplants, particularly bone marrow transplantation, where it's important to match HLA as closely as possible. Also, it's common knowledge that even with the most successful transplants, these transplants fail after 5 to 10 years, because even though we can suppress the immune system with immunosuppressives, we can match HLA, there is still a low level of chronic rejection that goes on, that eventually leads to occlusion of the blood vessels servicing the transplanted organ, that eventually it doesn't get enough oxygen, and so these people need to get another transplant. So first of all, with regard to the types of grafts in terms of nomenclature, the most successful type of graft is where you are grafting one part of your body onto another, as in the case of skin grafts. So people who get, say, massive burns on their upper torso, they will try to pad out the skin on the lower trunks, the silicone pads, cut out that bit of skin, and then graft it onto the damaged area. The other type of modern technique now is that we are able to grow skin in the laboratory. And so once several tissues, several layers of skin are made, this can be packed onto the affected areas. Then the other type of successful graft is what's known as the syngeneic graft, and this is where you get a graftment between a relative who is very genetically related to you. So the closest would be an identical sibling, like an identical brother or sister, which has a higher chance of success in engraftment compared to if you got the graft from your mother or father, because you have paternal or maternal HLAs that are recognized. So the syngeneic graft is the most successful and the highest chance of being accepted. Allogeneic graft is classical rejection scenario where you're receiving a graft from someone who's totally unrelated to you. And so because of the HLA differences, your immune response will react to that and reject it. We can overcome this by using immunosuppressive drugs to block that immune system reacting. And then finally, the one that is under intense research at the moment is what are known as xenogeneic grafts. And this is where we are taking kidneys, hearts, lungs from another animal, particularly pigs, because the size of their organs are very similar to the human size of the organs. And so this is, and the reason for this type of research is because there is such a lack of donors for these transplantations. So there's a lot more progress now with regard to this in genetic grafting, where through genetic engineering, they can humanize these donor animals. So in other words, insert the expression of human HLAs on these donors. And so this has much higher chance of being accepted. Sorry, with my voice, my hearing's also gone.
I was just asking you, which one's the most successful? Because you said that the autologous and the
Yeah, autologous and syngeneic.
successful.
Yeah, well, the most successful obviously will be autologous. Syngeneic has a higher chance compared to allogeneic. All right, but syngeneic, even though I said if you get a graft from your identical brother, you will still react to male expressive genes. These are called minor histocompatibility. So you will still have a low level of reactivity. Also, even if you have an identical sister, there are still minor genetic, even though you're essentially clones, you're not exactly clones because there are minor genetic differences between these individuals. So you can still get reactivity. So in these early days, with regard to the pure immunologists, through their experiments, they came to realize that there was some defense mechanism happening in the recipients of these skin grafts, which was reacting against this transplanted skin. It can be shown in this experiment here, where we take two strains from mouse, a green mouse and a blue mouse. And if you cut off a bit of skin from the green mouse and graft it onto the blue mouse, you find that after 10 days, that graft starts to necrose. It's not getting enough blood, the tissue gets destroyed, and the graft falls off. And that takes up to 10 days. Now, if you take blood from this blue mouse and inject it into another blue mouse, and then try the experiment again, where you graft some of this green skin onto the blue mouse, you find that rejection happens a lot quicker. Instead of 10 days, it gets rejected after 3 days. So it means that this immune system that activates these green mouse reactive lymphocytes are transferred into a new naive blue mouse, such that when it receives the green skin, these reactivated lymphocytes will immediately start to attack that engrafted green skin. So this shows that this displays memory. And it's specific because if you try this experiment again, where you then graft skin from another strain of mouse, in this case a gray skin, onto this adoptively transferred blue mouse, then it displays a primary reaction where rejection takes 10 days, just as in that primary response, compared to the secondary response. So it's antigen specific. And then another level of indication that rejection lay with the immune system, particularly T lymphocytes, is the fact I've told you about this before, is that we, through genetic engineering, we can create these so-called nude mice which don't have a thymus. And not having a thymus means that they lack T cells. And because of that, when we do the skin graft, we can graft skin from different types of animals like humans, reptiles, etc. And we find that even though this gets rejected, it takes much longer compared to the standard 10-day type reaction. So based on that, the early types of tissue typing techniques involve mixing blood, i.e. lymphocytes, from a donor and a recipient and see what happens. So remember, what's the point of the thymus? What is the thymus? The primary lymphoid organ, where your naive T cells which come through the bone marrow get educated, emerge as naive but mature T helper cells and cytotoxic T cells. So if you remove the thymus, that process doesn't happen. So all your T cells are essentially immature. They're not functional T helper cells or cytotoxic T cells.
How did it take longer?
How does it work? Okay. So now consider this. I told you last year about when a naive T cell gets activated. How does it get activated? Think in terms of antigen. So it sees antigen presented on MHC by your antigen presenting cell, your dendritic cell. Remember, you also needed those co-stimulation molecules CD28B7. So now this T helper cell becomes activated from the naive T cell into an effector T cell, right? What are the characteristics of an effector T cell in terms of function? What happens to that T cell once it gets activated as a result of seeing antigen? It functions by making cytokines, right? If it's a T helper cell. but it also functions by being stimulated to proliferate, to divide, to increase in numbers. So based on these two characteristics, if we see that during a mixed, what we call a mixed lymphocyte reaction, that is an indication that there is immune reactivity or activation of those naive T cells to become activated effector T cells. Yeah. So in the first type of experiment, and this is looking at function, so this is looking at cytokine production from activated T helper cells or increased cytotoxic activity of CD8 positive cytotoxic T cells. So in these type of experiments, we try to look at reactivity or MHC mixing between a donor, in this case a donor X, and the recipient, in this case donor Y. Right? In this type of experiment, what you are looking at is the activity of the cells from donor X to react to the HLA on these cells of donor Y, right? And so essentially, you are making the cells of donor Y a target. You don't want it to be reactive in terms of making cytokines or proliferase. You just want it to express HLA to be seen by the cells of donor X, right? So what you do is you bombard the cells of donor Y with a moderate level of X-rays. And what these X-rays do is they break up the DNA of the lymphocyte of donor Y that prevent that cell from functioning in terms of proliferating or making cytokines. So it's essentially just inert. The amount of radiation these cells get isn't enough to kill the cells, but it's enough to prevent those cells from proliferating or from functioning to make active cytokines. So basically, these are just neutral cells expressing the HLA donor Y. So now you mix these irradiated cells with the live viable cells of donor X. And if there is an HLA mismatch, so the HLA, the foreign HLA proteins of donor Y get presented on the dendritic cells of donor X and present these foreign antigens to the T helper cells and cytotoxic T cells from donor X. And so donor X cells get reactivated because they're seeing these foreign HLA antigens. And in this way, then, when we get reactivity, we can see this in the form of increased production of interferon gamma by the activated CD4 T helper cells, and we can see increased cell death of donor Y cells as a result of cytotoxic T cells from donor X attacking these foreign HLA cells. So we can see a reduction in cell viability. And this is the basis of the mixed lymphocyte reaction. This is one of the earlier techniques they used to determine whether a donor was compatible for donating tissue to a recipient. So this is based on function, as in cytokine production or cytotoxic T cell production or cytotoxicity. The other consequence I told you about in terms of T cells being activated when they see foreign antigen is that they proliferate. So similar to this mixed lymphocyte reaction, we can also measure alloreactivity by measuring whether these activated viable lymphocytes proliferate as a result of seeing allogeneic HLA. And so similar to the previous experiment, we irradiate the target cells of, say, the recipient, mix them with viable cells from the donor, and if there is HLA mismatch, the donor cells will start to proliferate, and this can be measured either by counting the cells to see an increase in cell numbers or adding radioactivity, which gets incorporated into the DNA as a result of DNA replication. So an increase in radioactivity, an increase in cell number tells us that there is alloreactivity against the target. And this can be seen here by the graph. So this is dendritic cells as a control. So this is just dendritic cells being mixed with the same T lymphocyte from the same individual. So basically, there's no reactivity. The T cells are seeing the same individuals in antigen presenting cells. So there's no increase in reaction. But here, where we are seeing foreign antigens from a donor being presented to the functional T cells from the recipient, we see an increase in proliferation. And so that shows an allogeneic response. And so in this way, we can get a readout. And in this example, let's say we have a recipient who needs a kidney transplant. And there are 3 potential donors, father, mother, and a sibling. So we mix the cell from the recipient, and so this is the control here. So this is essentially just an autologous reaction where the cells, target cells, the recipient, are mixed with active cells from the same recipient, and there's no reaction. So this, the degree of radiation is baseline at 1. If we mix the recipient cell with the father's cells, we see that this amount of proliferation jumps up to 4. So that shows that the father's cells are being activated and proliferating and being directed against the son's target cells. The same with the mother. And now with the sibling, we see that there's the same level of baseline non-reactivity. So this conclusion then tells us that the sibling is the best donor to give a kidney to the recipient. Right? So just look at the numbers. You see an increase in numbers, bad. Low level number, that's fine. Right? So the problem that the surgeons, the human clinicians had with trying to understand the mechanism of what were the conditions which allowed for the acceptance of a graft or rejection. The research was very slow, and the reason for that is because as normal populations, we are essentially a mosaic of the HLA through recombination events that we inherit from our ancestors, from our parents, our grandparents, great-grandparents, so on. So each of us have a very mixed pattern of HLA genes that we inherited through generation because we are an outbred population. what the classical immunologists did was that they collaborated with mouse breeders. And what these mouse breeders did was they took, say, two strains of mice, and they bred them to give brother and sisters. They then mated the brother and sisters, and that generation they did the same brother and sister mating. And they did this over 50 generations. And essentially what they're doing through this process is diluting out all of those foreign genes with the different members. So essentially, after 100 or so brother-sister matings, you essentially come out with a pure clone of a strain of mice that has a uniform genetic pattern compared to its others. And these strains of mice are still being used in immunology research now, even though they were developed over 100 years ago. From these pure strains of mice, we could then dissect the different patterns of rejection or acceptance. So in the first panel, essentially this is what we get when we do an autologous graft or a genetic graft. And what they do is they take a bit of skin from this strain of mouse, strain A, and transplant it onto another mouse of the same strain, strain A. And you find that this engraftment takes and there's no rejection. If you then try to transplant a bit of skin from strain B into strain A, then you get what's known as an allogeneic response, and you get rejection after 10 days. If you mate strain A and strain B, so now the progeny is expressing both A and B HLAs, right? And you transplant skin from this pure one strain, strain B, into that hybrid A-B strain. That also isn't rejected. Try to figure out why. Because the B antigens are going into this hybrid which has both A and B antigens. And even though this has A antigens, that isn't an issue because we are reacting against the donor. So the B and the B are compatible. So there's no rejection. But if you do this the other way around, where you try to transplant the hybrid A and B into a single genotype strain A, that recipient strain A is seeing these foreign B HLAs and attacking. So you're getting rejection. So in this way, this is how we devise what are known as the rules of transplantation. So just to jog your memories about HLA, remember that there are two major classes, class 1, which consists of 3 subgroups A, B, and C, and class 2, which consists of DP, DQ, and TR. The characteristics of HLA is that they are codominant. So that means that you are expressing, all your cells are expressing both class 1 in terms of nucleated cells from the 3 A, B, and C antigens from both your mother and your father. So both chromosomes are expressing the same, right? And class 2, which is predominantly on cells involved with the immune system, like antigen-presenting cells, lymphocytes, and so on, In addition to expressing class 1, you also express in class 2, DP, DQ, DR from your mother and father, which means that cells which are involved in the immune system, like dendritic cells, are expressing a total of 12 HLAs, 6 from class 1 and 6 from class 2. That's a favorite MCQ question of mine, so as you haven't noticed. Now, so in addition to those functional tests to determine compatibility through this mixed lymphocyte reaction to look either for cytokine reduction, proliferation, or cytotoxic killing, we can also do this by with now the routine genotyping of our cells. We can look at the genotypes to see whether we have a good match or not. And this is shown in this here, where for kidney transplants, essentially they only looked at 3 of the classes of HLA, 2 for class 1, A and B, and 1 of the class 2, DR. Don't ask me why, but this is what transplant surgeons tell me, and I wouldn't test you on that. Remember, because the expression is codominant, we're expressing 1 allele from the mother, 1 allele from the father. Right? And it doesn't matter in what order these alleles are. So in this example, we have a recipient whose HLA genotype consists of HLA-A, where you have allele 3 and allele 8, HLA-B, where you have allele 1 and allele 8, and DR allele 3 and allele 4. So what you want to do is match up those numbers, those alleles, with the potential donors, where you want to get as close a match as you can. So in this first one, where we are looking at, say, 3/8, 1/8, 3/4, to the first donor, right? So we see here that these, in HLA-A, that is identical. There are no differences, right?
Yes.
Yeah. With B, we see 1/8 and 1/27. So that means that there is 1 difference here. With DR, we see that 4 is identical, but 3/8 is different. So that gives us a total of how many differences? 2. Right? Now work it out for yourselves. With donor 2, how many differences do you see? 3/8 versus 8/6. 1 difference. Because 8 is identical, 3 and 6 is different. That's 1 difference. Here they're totally mismatched, so there's 2 differences there. That gives 3. Another 2 differences there. So a total of 5 differences. So work out the others. How many differences was donor 3? 3? Yeah. Donor 4. 4, 2, and 1. 4. And finally, donor 5.
1. 1.
1 or 2? 1.
So it's just not mismatched at all.
What about the 8 and 27? Yeah, there's 27, and then there's 33.
We're talking about donor five.
Yeah, yeah. So HLA is 33.
HLA 3/8, 3/3.
That's one.
So the threes, there's no difference here.
Both of them. Okay.
All right. And 8, there's one difference there. 3/4, remember I said the order of the numbers doesn't matter. So the conclusion for this then is donor 5, you can look up that to be and stick it into the research here.
So instead of being 3, it was, for example, 3, that would be considered a two return.
Yep.
So if it's the same number twice, that's probably different.
If it's the same number twice, then it's this type of scenario. Right?
The best donor is 1.5.
Yes. Okay. So when we see graft rejection, the intensity of the immune response rejecting that organ is much higher than when you get an inflammatory response as a result of bacterial or a viral infection. And there are several reasons for this. One is antigen load. Imagine that if you transplant a solid organ like a kidney or a liver into a recipient, and if the HLA is not compatible, you are sticking in a massive amount of antigens into the recipient or being detected by the immune system. Compared to even a full-blown systemic bacterial infection, number of cells that you're putting into the body is much higher. So the antigen, because of the antigen load, your immune response is a lot more intense. The other consideration is that many of these HLA genes have resemblances or similar antigenic specificities to the antigens that the recipient has encountered through its lifetime. So many of these HLA antigens can cross-react with any bacterial or viral infections that this person has gone through. So this adds another level of immune attack. The other consideration is that, remember, in the process of primary education, when your naive T cells are passing through your thymus and seeing your self MHCs, remember, if they bind to the self MHCs too strongly, they will die. If they bind too weakly, they will die. But when you are putting in totally foreign MHCs into the body, those T cells haven't been exposed to those MHCs, so they haven't undergone that process of clonal deletion. So this is another level of waves of immune attack. Sorry? Yeah. That's an interesting question. I guess it depends on the age of the kid, how developed the immune system is in terms of being exposed to these different antigens. But so essentially, I couldn't answer that. But there's another thing too you should bear in mind, that there are certain organs, particularly the liver, for some reason which I still haven't been able to find out, HLA compatibility isn't as big an issue compared to other organs like heart, lungs, or whether there's a lower level of HLA expression on these, I don't know. Just be aware of that. Now, don't focus too much about this slide, but again, just be aware of it. There are two types of antigen presentation when you are transplanting an organ into a recipient. Because remember, when you are transplanting an organ, that the blood vessels in that organ still contain immune cells from the donor. And this includes antigen-presenting cells like dendritic cells, as well as the donor's T cells. So we have two types of antigen presentation. One which comes from the donor's dendritic cells presenting the donor's MHC antigens to the recipient's T cells. And this is what is known as a direct recognition. The other is where the donor's MHC antigen get picked up by the recipient's dendritic cells and then presented to the recipient's naive T cells. And that is known as indirect presentation. So we're getting antigen presentation by the donor's organ or the donor's tissue. And also in the indirect recognition, we're getting antigen presentation by the recipient's dendritic. The difference between the two is that with the indirect recognition, where the donor's dendritic cells are presenting donor's HLAs to the recipient's T cells, there's a stronger immune response of both cytotoxic T cells and T helper cells, which get activated to attack the donor's HLA. But in indirect recognition, where the recipient's dendritic cells are picking up the donor's HLA and presenting it to the recipient's T cells, essentially only the T helper cells are activated, not the cytotoxic T cells. And so rejection occurs through cytokines only, and not through cytotoxicity. So as I said, with the advent of immunosuppressives, we don't worry too much in many types of organ transplantation, particularly kidneys, for HLA match. But there are certain types of grafts which involve very close match. That is in bone marrow transplantation. Do you learn about bone marrow transplants at any stage? Keep on block or anything like that? So you know that bone marrow transplantation, essentially what you're doing is establishing an immune system of the donor into a recipient where you block all of the existing immune cells. And because of this, if you don't match the HLA properly, you can get a full-blown autoimmune response in the form of graft versus host reaction, where the reconstituted immune system of the donor starts attacking the recipient's HLAs and all the cells. And as I said, even though you can match HLA quite closely with regard to, say, genetic functions between an identical twin or whatever, there are still minor individual differences in genotype. This is in the case of, say, Y chromosome expressing antigens from a brother who's donating into a sister. So, and these are called minor histocompatibility antigens, and they are also a source of immune reactivity, which can lead to chronic rejection. Another thing to be aware of is that the health of the donated organ plays an important role in terms of success of transplant. And this comes with the idea of dams. Remember, if there is some damage to the cells in that donor organ, it will release dams and so initiate an inflammatory response, upregulation of adhesion molecules, and so on. All of that helps to activate an inflammatory response once it is transplanted to the recipient. So a lot of research has been developed into trying to develop the ideal conditions for preserving an organ once it's been taken out of a donor, because in many cases, this organ has to be flown across the country over 3 to 5 hour flight. So it's not just easy just packing it with ice. You also want to flush it with physiological fluids and so on to maintain physiological balance. Now, finally, there are different types of rejection mechanisms, and for this, you need to recall the lecture I gave you about the different types of hypersensitivity reaction. In particular, type 2, type 3, and type 4. So we have hyperacute reaction, acute and chronic rejection. Hyperacute is predominantly a type 3 hypersensitivity reaction, which involves antigen antibody complex. Right? The target in this immune destruction is generally not just the parenchymal tissue making up the organ, but also the endothelial cells which fuse through that organ to supply the blood. So a lot of that damage occurs on the endothelium. By doing that, you then preventing enough blood to diffuse through that organ, so it will just die through oxygen starvation. So with acute, it's particularly a problem, even though you've matched the HLA gene. In many cases, if a recipient, one, has either received multiple blood transfusions, two, has received transplant procedure before, or in mothers who have had multiple births. What these different conditions will do will, because you are putting in, because these people have been exposed to foreign antigens, as in the case of multiple blood transfusions, someone who's received previous transplantation procedure, or a mother who's received multiple births, because with every birth, you are getting new paternal antigens which are being presented to the pregnant mother. And with all of these recipients are developing antibodies against these foreign antigens. So you have already preformed antibodies against these foreign antigens. So if you transplant an organ into this sort of person, these preformed antibodies will immediately bind to the circulating foreign HLA antigens, cause immune complexes deposit on the endothelium to activate complement, and so you can get rejection within hours. And this is why it's called a hyperacute rejection. Acute rejection is the classical allogeneic response, and this involves both a type 3 and a type 4, type 4 of cell immune response. The T helper cells recognizing allogeneic antigens being activated to produce inflammatory cytokines, as well as cytotoxic T cells attacking that foreign tissue. And then finally, chronic rejection is in the case where I said in many cases, in most cases, people who receive successful transplants need to be transplanted again after 5 to 10 years. And this is because of these minor histocompatibility antigens, which are slowly activating these cell immune responses, which are causing cell damage, repair to that damaged tissues through IL-10 beta. You get scarification of the blood vessels, eventually getting occlusion. So these blood vessels get blocked up and they can't produce enough blood to supply that organ. This is just a repeat of what I've covered, and that's it. Any questions? Right.
Doctor, I had a question.